here. So I will use some of these polls, some here and there, just to keep the activity going. So C was correct, which most of you also said. So if we take the question there, how do you know and why do you guess it would decay as 1 over the distance square? Can you give me some arguments why that is happening? Anybody who feels free of speaking, just say something. Is it someone who is guessed C and think you have an idea why it decays like that? If we can take some, I can see there are also now coming more people have to let in here in waiting room. Hopefully that will be solved if you log in to Zoom with your Lund University ID. If you give those credentials to it, you should go in directly. Yeah, and a good answer from one that you remember a formula. That's really good. There is nothing wrong by remembering anything. Of course, understanding why it is like this is slightly better. So if we take from the thing that you can see here, yes, you look at the unit of this one. Why would that suggest that you go over 1 over meter squared? Of course, there, if you look at the unit of this one, you have the unit, which is watts per meter squared. And the decay here, 1 over R2, how do you measure distance in meter? It really fits the formula. And think what you're doing. You are transmitting a certain amount of power, watts, that's propagating away. You ask what the density is, which means how many watts are there per square meter. You get the units to work correctly if it decays over 1 over R2. So that's, of course, one thing of seeing it. It doesn't maybe give you the really fundamental of understanding of why it happens, but it is in the right direction. So if we think what's happening here is that you propagate now your, your power in these cases. So let's say here that, let's see if I can draw this, that you here transmit, say 1 watt. And then you see what is happening when you surround that with the surface. Of course, this wave will propagate out through this surface. Let's assume it's a sphere. And if all the power is equally distributed over this sphere, what is then the power density? Then you would just take in these cases and say that, yeah, that is the transmitted power divided by the area. And if you take the power, you divide by area. What is happening in those cases? Yeah, then you get a unit here, which is 1 over meter squared. And you get the decay over 1 over R2, because the area of the sphere is the radius of the sphere to the power of 2 divided by 4 pi. So it's 4 pi R2. So that is the area of the square of the sphere that we have. So in some ways, what's happening here is just, it's a geometrical factor. It's spreading out in 3 dimensions. It's divided ourselves of this spherical shell. And how big is the spherical shell? That's the area of the sphere. Area is meter squared. And then, of course, the radius squared, 4 pi. So it has to decay over 1 over R2. That is in some ways the simplest argument that this actually is happening. We will show it further on that this is what's happening. Yeah, so it decays of 1 over R2. One thing more with this, I haven't really talked, and we will not talk about acoustic waves, but if the power decays over 1 over R2, this is a pressure wave, that is the field, then the field decays as 1 over R, because the power is the field squared in some ways. We will see exactly the same thing in electromagnetic fields. They will also decay over 1 over distance squared. The electric field decays as 1 over the distance. So if we want to just argue this, exactly what I did, if you take and assume a source transmitting power 1 watt and is radiating isotropically, So equal in all directions. And if you have a small acoustic source, it actually radiates the same way in all directions. So when I'm speaking here, I'm speaking a little bit more in this direction, but you can actually hear me also on the backside. If you took a small, loudspeaker, you have it very small and round, it basically radiates all around the case. So acoustic waves is actually radiates equally in all directions, which we will see that antennas do not. They are different in that case. And then the wave propagates away from the source. The source is at point 0. In this course, I denote vectors here with boldface notation here. So this R is that you are in the center of the coordinate system. And then this total power P0 passes through a spherical surface. The spherical surface has an area 4 pi r2, radius r. Then you have the power density, just divide the power with the area. That is watts per meter squared. And you can see that the power density here decays over 1 over r2. So this will always happen. This is how it decays. And it really has nothing to do with acoustics. Its electromagnetics are the same. All waves are basically the same in this type of settings. So it's really good, as we say. Yes, you could memorize these things. But if you don't memorize it and you don't understand, if you instead understand it, you will always remember it and you understand what it comes from. And it's so simple to derive, so you can basically do it in your head. Of course, you have to know a few things. What is the area of the spherical surface, for example, which I hope you know. So now if this was in a two-dimensional setting instead, imagine this is like a long cylinder, infinitely long cylinder radiating out. What would the decay be from a cylindrical case? How does the power decay in that case? Then you have to do exactly the same thing. And then you can see, of course, it's invariant in the height direction. It's a huge cylinder. So it only decays and spread out over the circumference of the circle instead, which is 2 pi r. So the decay in a 2D is instead 1 over r, because it's a circumference of the sphere. And we have exactly the same thing again for electromagnetic waves, acoustics waves. Just a geometry factor, that's it. So then we start studying these plane waves, or waves, we can say in some ways. So here you can see one case of a wave. The wave is propagating here in one direction. A typical way that these waves looks like is that they have some amplitude. So electric field, we call it E0. When we go to the electromagnetic fields, it will also have a direction. I will do that soon. And then some time harmonic type setting here. You have some angular frequency omega here times t minus kz. K is called the wave number that sits there. And the angular frequency here is related to the wave number with the velocity of these ones. So if it's an electromagnetic wave, the speed of light. And the frequency is related to the wavelengths. So if we take this wave I have here, how do we know that it propagates to the right? You can see it in this picture here. It looks a little bit fast and wobbling in my view here. I don't know if I can reduce the speed. Never mind. It's probably the viewer. So this propagates with no decay in the z direction. And in these cases, what it means is that if you take your t and you increase it, so you want to see where does this propagate, that means t is going forward. That means that you need to increase z. So if you think here that I want to keep this at a fixed point, then if I increase t, I need to compensate by z. So z is increasing and t is increasing, and it's a minus sign there. If it was a plus sign, it will go in the opposite direction. So the parameters then we get out of this one is, for example, the wavelengths. And the wavelengths here, what does it mean? It means that the 2 points here are the same. So the distance from there to there. Okay, that is that cosine omega t kz is equal to the same thing when I add lambda. And of course, if these is going to be equal, it means that k lambda has to be 2 pi. It could be a multiple of 2 pi's too, but the shortest one is 2 pi. And this is the same thing as if you had in when you do it in the temporal variable, and there they had the period time, which has omega t is equal to 2 pi. This relationship I know you have seen in many, many courses because you have studied a lot of cases with evolution in time. In this course, we will be more focused on evolution in space. And there we have these wave numbers, we have the wavelength, and they are related with these 2 pi. So sometimes I will talk about what is the wavelength, sometimes I will say what is the wave number. We will use both. In the same way as when you do this in time, sometimes you talk about angular frequency, sometimes you talk about the period time, because sometimes one is convenient and sometimes the other one is convenient. And of course, in time, you usually also have the frequency, which is the 2 pi difference from the angular frequency. So these are the relationships that we have in this type of waves, which we will use. But now we will do it for electromagnetic waves. And I know that some of you have studied electromagnetic fields before, some of you have not. So it's not a pre-requirement to have done this before, and we will not really use the explicit knowledge of how to solve these equations. We will do everything we need in this course. But of course, it's good to have some background how these antennas are actually used together with this electromagnetic field, because we cannot have antennas without talking about the electric field, for example. We need magnetic fields. We need the electric current density. In most cases, we actually only need this one. And actually even more, in most cases, we only need this one. But we of course need to know what they are related with and what they are. We will use them quite heavily, especially the current density. All of this goes back to Maxwell's equations, which are these equations here. And J is then the driving current to these cases as we have it here. And then we can have these fields, electric field, magnetic field, and electric field. And the difference here between, for example, E and D is due to materials. That's it. But in all of those cases, of course, we need kind of solving this. And we will use the simplest way of getting out the solution for this, which we will actually do in this course. One thing that's come out of this is that we need to talk about where the energy flows. And that's coming from something called the Poynting vector. And by definition, that is the E field cross-multiplied with the H field. And maybe not everybody here now is familiar with this notation. I will show you on everything we need to do by this one, what it is. It's a multiplication between 2 vectors. The Poynting vector here, you can see, have a dimension of watt per square meter, which basically is our energy density. But it also have a direction. So this points in a direction. I will show you a right-hand rule of this very soon. And then we, of course, have our parameters I talked about. So we have the frequency, the angular frequency, the wave number, and the wavelength. And one thing here is that we will jump between this. So we need to have some kind of idea what these parameters actually are. In free space, there come some important numbers. So impedance of free space, this eta 0 here, is approximately 377 ohms. So it's just a number. It's like a number of nature. The same way we have the speed of light, which is approximately here 10 to the power 8 meters per second. So incredibly fast compared to the acoustic speed. And then there are some material parameters which we don't really use in this course, but sometimes they might show up in some formula. And that relates some fundamental properties between the E and D fields and the H and the B fields. And most of this course, we will talk about what's called time harmonic fields. So the time E of t here can be written as some E that depends on frequency times e raised to j omega t. And when something is time dependent, we explicitly write out t, which is very rarely in this course. Most of the time, we will talk about the frequency components of it. So now if we move down to our electromagnetic waves. So before the break, we just talked about acoustic waves. Now what happens in electromagnetic waves? The speed of light, you all know it. That's also a number you learned by heart. It's 10 to the power of 8 meters per second. Compared to acoustic one, incredibly fast. It's approximately 10 to the power of 6 times faster. So if you think about it, I talked about this 15 milliseconds. it takes to propagate 5 meters. Think in a regular classroom, the distance between me and where you would be sitting. The electromagnetic waves then instead propagate 4.4 10 to the power of 6 meters, which is approximately 70% of the distance to New York in the same time. So incredibly different, but the underlying structure is very similar, but the speed is so much faster. So really a lot of things happening here. And what this actually is used for in many cases is that you have a very low delay, latency you can have in systems where you even process this, because it doesn't take that long to move the signals. If you think about some of ideas for 5G that's coming, is that you should be able to sit, for example, in Lund and drive a truck in Malmö or do some surgery. If you did it with an acoustic wave, you can never do it, because the distance from Lund to Malmö would take so long time for the sound to propagate, so the delay is too long. But with an electromagnetic wave propagating at the speed of light, you can do it because it's still short. The speed of light is also the upper limit for any information. So you cannot transport information faster than this. So it sets some limit there. And of course, in many cases, it's sufficient. You know, Malmö-Lund, it takes no time at all. But as we said, to go from New York to Lund here, probably around at least 20 milliseconds, which actually is quite long. That's a delay that we can live with in some cases, but not always. And then, of course, you would need to process this, that adds times afterwards, because it should go into electronics, something should happen and so on. But it starts to take time. If you talk over the phone over a satellite and you talk to a person, for example, in Australia, you know, you can go over a satellite link, you actually have a delay in that communication, because actually the distance starts to be long. If you run a space shuttle somewhere, it takes so long time for the information to travel to it, because the distance is so long. So you actually have to wait. You send a message, you have to wait quite some time before you can get the answer back, which means you cannot automatically control something. You cannot say, oh, there's coming something, turn right, because it's too late when you say turn right. The wavelengths in the electromagnetic waves spreads in the same way as an acoustic wave over a huge area, larger than acoustic one. If you think about typical frequencies here, think 1 megahertz. That would mean that you have a wavelength of approximately 300 meters. So of course, speed of light here divided by the frequency. 300 meters is quite long. If you go to 1 gigahertz, 3 decimeters, pretty good. And this is now one thing that actually is really good to learn by heart. Because when you do this calculation, all of you know, how do I calculate the wavelengths? Okay, speed of light divided by frequency. Okay, so what is then the wavelength for 1 gigahertz? 3 10 to the power 8 divided by 10 to the power 9, put it into your calculator, wait for an answer. Okay, 0.3 meters. If you instead learn this by heart, that 1 gigahertz is 0.3 meters, and you start asking, okay, what is the wavelength for 30 gigahertz? How do you calculate that? You don't put it into this formula here. You just take your 0.3 meters and you divide it by 30. So much, much simpler in these cases. It's 1 centimeter. And when you think about antennas and communication systems, most of them sits around 1 gigahertz. So it's very, very easy to normalize to 1 gigahertz. And then you can get all these length scales directly in this communication band. So you say 60 gigahertz. Okay, how big is 60 gigahertz? That's half a centimeter. No calculators, nothing. Because you can all divide in your head 0.3 in this case with 60. And you can get it out. And then you can actually understand, because what we will see is antennas like to be half a wavelength, which means that they will give you a reference to the size of these antennas. If you go to optical frequencies, you can see here we're in micrometer range. So around half a micrometer, 10 to the power of -6 meters. And all of these are waves or wavelengths that will build antennas. But of course, if we want them to be half a wavelength, it's pretty hard up here, because here it's like 150 meters. Down here, it's really tiny. So maybe we need different types of antennas for this because it's hard for us to build them. But the wavelength is actually the most important parameter for an antenna. If we look at bandwidth of this, think about, especially if you're in communication here, if you want to communicate, the best thing you can have is to have a lot of bandwidth. If you sit around 1 megahertz, it's really hard to get bandwidth because when you talk about communication, it's absolute bandwidth. And okay, let's say you have half a megahertz of that. What does that mean? Then you would go in bandwidth from quite a distance here. You would cover basically everything around 1 megahertz. But if you take 1 megahertz around 30 gigahertz, it's basically nothing. It's extremely narrow band, but it's the same absolute bandwidth. So when you go higher and higher in frequency, you have more and more bandwidth available, which means you can have more, higher data rates, which is one of the things that comes in 5G when we come to millimeter waves, because we go up so high in frequency, so we have a lot of spectrum up there. And then an important thing for electromagnetic waves is that they are not like our acoustic wave. They actually have a direction. They are vector fields that change quite a lot. We will see it a lot in this course, that they point in a certain direction. And the thing that comes in many cases is that materials typically reduce the speed of an electromagnetic wave, and where this refractive index comes in, so it goes slower in the material. And if it goes slower, it changes the wavelengths. And that we will see that we use when we design antennas. So this is some basic properties of electromagnetic waves. And this is then how a typical electromagnetic wave would look like. If this one would be playing. Okay, maybe it doesn't want to play. Okay, it should be moving. It was moving before. So this would be an X-polarized plane wave propagating in the Z direction. And here we can see that the electric field then go in this X direction here, up and down, while the H fields goes in this direction. So they are very different now from our acoustic pressure waves, which are scalar waves. These are vector waves. They point in a direction, which of course, when it comes to antennas, if you take a dipole, it looks like a long line, which means this span has to be oriented according to the electric field. And then, yeah, in the same way, we can write up this electric wave. We have the same thing in the scalar one. A typical way is to say there is cosine omega t minus kz. So again, angular frequency, wave number. So the wave number is the same parameter in space as the angular frequency is in time. And we have the same relationships then between the frequency and wavelengths, no difference here. And one thing that happens here is that we have a simple relationship between the magnetic field here and the electric field here, and that is this free space impedance that sits here. And it looks like this actually is moving, but very slowly. Maybe it's my computer, I don't really know. But you can see that it's not the speed of light this one is moving. It should be faster. And this one is now propagating in the Z direction. So again, increasing T means increasing Z. So it goes in the Z direction. And this one is now related to one of the fundamental properties as I had when I mentioned this pointing vector. And that is this right-hand rule. So if you're not familiar with this cross product, what the thing is that you need to know about it is that if you take your right hand, they are in an ordered fashion here. So if you take the one that you can see in the picture there, you put this finger in the A direction, you put this in the B direction, then the cross is perpendicular to both of them. And what's happening here now, if I take E cross H, then I should put this finger up because my E was there, my H is then towards me, and my thumb points to the right, which is what we have here, if I just turn this figure. And that is an important property because in this course, we will be in the far field of our antennas. And in the far field of the antennas, E and H and the direction of propagation have this property. So if I know where the direct wave is propagating, I know where my E field is, I know where my H field is pointing, and so on. And I know that it's always propagating away from the source, so I know where basically my thumb will point, which means my E field can be anywhere there, and then I have to look what the source has for properties. And that is something that even if you have not seen these cross products before, you don't need to, but you need to have this intuition about the E and the H fields. They are perpendicular to each other, and the cross points in the thumb of this direction. And that we will use. So then I talked about this spectrum before. So if I now write up the spectrum that we basically have, which is available for us, we can take low frequencies, which is the lowest frequency you could think about. It's basically 1 Hertz. And is 1 Hertz fast or slow? I guess it depends. 1 Hertz means 1 per second. So once per second for a human being is pretty fast. But in most other properties, it is incredibly slow. If we go to the highest frequency here, we count with electromagnetic waves, it's approximately 10 to the power of 15. There it starts to happen other things. That's visible light, basically. So we are spreading around here. Our cellular communication, most of it sits around here. And then, of course, it's interesting to see what is the wavelength here. Because then if I have the frequency, I have the speed of light, I can calculate what is the wavelength. So speed of light divided by frequency. So the point up here at 1 is then 3 times 10 to the power of 8. And then we can go up here to 1 kilohertz, 1 megahertz, 1 gigahertz, and so on. We can go down. And then we can start asking, okay, I would like to use these frequencies. And then if we start thinking, your device should be around a wavelength, like half a wavelength antenna. How big does it have to be? Yeah, 3 to the power of 8. What is that big? Is there anything around us that has that size? Think for a while. What could be that size? Actually, there is something which is of that order at least. And what is on that order is Earth. So when you actually look at the Earth, it is really like somewhere down here in size, or here in size of this one. Which means that you would get some resonances around these frequencies. And one of those that we can actually demonstrate and see is called Schumann resonances. They can be measured. If you put up here instrument and try to measure the spectrum, you will actually see quite a lot of activities here around, I think it is 7 Hertz. What is that? That is actually thunderstorms going around the equator. Thunderstorms is an electromagnetic field. They generate an electromagnetic wave around Earth, which is resonant around 7 Hertz. It's a resonance of Earth. We can detect it. But of course, if you would like to build it, it's pretty difficult because we cannot build Earth. We have Earth in some ways. So that's not where we sit when we would like to use something. If you go up in frequency, you can go above here, go above 1 kilohertz here. You go to a band that's called the VLF, very low frequency band. And you can ask, do we use that for something? This is actually used. One of the use of this today is actually submarine communication. Very low frequencies. It's also the original frequencies that were used to communicate over the Atlantic. For example, from Europe to the US, they are down here. They have huge antennas. Here you can see the size of these antennas. If you travel to Gothenburg, you actually pass these antennas. They are still up there. I will show them later in the course. If we go up a little bit higher, we have the one that sits in your LU card, for example, RF type antennas. And these are inductive type communication. So it's huge coils that sits there. And then you don't have a half wavelength structure. You have more, what I would say in these cases, and circuit type coupling. It's just inductive. When you go to gigahertz, you're pretty good, because 1 gigahertz here was like 3 decimeters. And we start thinking human devices, 3 decimeters, pretty good. Not that you would like to carry something that is 3 decimeter cellular phone, but it's of that order. It's something that fits humans in some ways. It's a good size for us. When you go up higher in frequency, so we start leaving these bands, we go to the millimeter bands. And they start in some ways formally at 30 gigahertz, because that is 10 millimeters in this case. And they go up there a little bit, and then comes terahertz. And here, actually, the devices are so small, so they are tiny compared to anything we care about, which means that if you would take a device, you could build an array there. So at these frequencies, you can actually fit, like you can see here, these are 16 antenna elements of a size which is approximately 1 square centimeters. And then you can build an array, and we will see in the course arrays have a lot of freedom because you can steer the beam, you can make it intelligent. You cannot do that at 1 gigahertz, and you would like to have it carried by a human because the wavelength is too long. If you go higher in this, you come to the terahertz band, which is actually one of those that's very hard to utilize at the moment. There's a lot of research going on. It's really hard because it's somewhere between like the optics and the microwaves. So neither of the techniques works really well. Infrared is a big spectrum that comes here. We, of course, have it lots of sensing. You can feel heat with it, so that's infrared radiation. And then, of course, we have the visible spectrum that comes up here, and then we're down to sizes here of micrometers. And when you think about your camera, that is an array, huge array, but the wavelength is so small, so you can have this array with so many pixels on a small size, because they can be down to a few wavelengths in size, each pixel. They fit that. Somehow similar to an antenna, but they only receive the power. They don't take any phase or anything. Going even higher, we're up to X-rays. And there are a lot of things that's happening. But this is the spectrum where we deal with. And we build antennas in all of this region. So some needs to be down here and some needs to be here. And they all can be like, half a wavelength in size. And then what is used for, you can of course look at how the spectrum is utilized. And some of you know about it, some of you might not. But spectrum is sparse. People buy it for different things. So every little piece here is used by something. So you can see here, if you go to 60 gigahertz, you're somewhere here. There's a lot of things that these different things are, already specialized for in some ways. Inter-satellite communication and so on. Mobile use and so on. So every little piece of the spectrum is in some ways used for something. And that's where our antennas sits. So what we will do now, we will see if we cover all material today, otherwise we will continue a little bit. Now we will actually talk about the parameters that we need to describe our antennas. So the first thing we have is that this pointing vector says how the propagation of the wave is going in some ways, the direction of this power. And if we do that, we compute E cross H, and we do it in the far field of an antenna. So basically I sit here, here's my antenna, I go out somewhere far away with it. It will always point away from where the antenna is. So if you are sitting someplace, you look at the antenna, the power goes away to the other direction, not the way you are looking at the source, just backwards. And that's of course happen everywhere you sit around these ones. And the radiation intensity that comes out here then is then related to the electric field squared and normalized with this free space impedance, because we saw that the magnetic field carried also this free space impedance to transform it to the electric field here. And the decay is 1 over R2, exactly as we had before. And this then go in the radial direction. And the radiation intensity then says, how is this power distributed around this sphere in some ways? So if we look at this dipole, very little radiation go up here. So here U would be 0. Most of the field is down here. So here U is very high. And it then depends on the spherical coordinate theta and phi. So different angles, different power comes out with. And the radiation intensity has then the unit of power per unit angle. So it's really in watts, but it's normalized to the angular resolution that comes out. So exactly what I said here, yeah, pointing vector is in the radial direction. It goes in this R, the cases are -2. The electric fields also propagating in this radial direction, so are always outwards, and they are perpendicular, satisfy this right-hand rule. So if we go in the thumb's direction, they are perpendicular to that. And the amplitudes here decay as 1 over R. So the same thing as we would have for this acoustic wave, my speech, exactly the same thing. And this will then let us define our antenna parameters. So again, the same type of antenna. We can see here radiating antenna, and you have the radiated field, and then you can ask what parameters are we interested in. So if I have this little dipole again, the movie should be playing, which it's not. We can then look at interesting parameters. And one of the parameters is, of course, what's happening in the transmission line here. So in this case, I'm interested how a wave here gets transmitted out. And I typically do that by looking at what is reflected back. And I want that nothing should be reflected back. That gives my S parameter of the antenna. And all energy that then comes into the antenna should be transformed to radiated waves. And this one then should propagate in the direction of the receiver. So a typical case here, which also should be in movie, I think it is if you open the PDF files. Here we then could see what happens on a line that goes to the antenna. And we can see what's happening is that one wave here is the incoming wave red, and one will be a reflected wave. And then we will have a reflection coefficient, which says the reflected wave is typically gamma times the incoming wave. And if I look at the sum of them, the amplitude is going up and down. So to then characterize our antennas, what we need is then the parameters for it. And the typical antenna seen from the electronics is just the antenna input impedance, which is the voltage divided by the current. And we will look at that typically as a function of angular frequency. In the lab, you will measure this for your own built antenna, and you measure it by measuring the reflection coefficient, so the S parameters, and then you can transform that to this impedance that we have. So the reflection coefficient is given by the input impedance normalized with the characteristic impedance of the transmission line, which is typically 50 ohm. All measurement cables here are 50 ohm. So we can either go from the input impedance to reflection coefficient, or from the reflection coefficient to the impedance. And you will measure this with this network analyzer. So that you will do in the lab. Standing wave ratio was one thing that we saw in this picture before, when a wave going up a little bit down. And this is a quantity that takes the quotient between those two. That's called a standing wave ratio. And it's also related to the reflection coefficient. When we look at the radiation properties, there we then have things that then depend on many different parameters. So for example, if I have a Tx and Rx, the distance and the direction comes in here. Typical cases here, we will write that the position of the receiver or the receiver point here is something in X direction, something in the Y direction, something in the Z direction. So for example, horizontal one, X, Y, and Z straight up. And then I can say, where is the receiver? I need to know the distance. Then it's just a square of all of those ones and the square root. And it's pointing in the direction here, which I just call R hat. The transmitted power comes in. Antenna properties, of course, in this direction. If they are aligned, the antennas, so if you have two dipoles, if they are like this, or if they are like this, comes in. Wave propagation, in this course, it's free space. And then what we have is that we have some radiated field from the transmitting antenna and some received power in the receiving antenna. And we will separate those two. And then we will just write up what quantities are. So the radiation intensity really says what the angular distribution of the radiated power of the antenna is. So if you think again, you see the antenna in here, how much power do you get in this direction compared to how much power, for example, in this direction and this direction. So here you will see that the radiation intensity is high in this direction. It's lower here. It's basically zero here. And the radiation intensity then depends on these angles, theta and phi, but also about how much power I transmit. And that, of course, depends on your electronics behind the transmitter. So to take this away, we actually define our first antenna parameter here, which is the directivity. And the directivity is then this radiation intensity normalized with the average radiated power. And average mean here like the total radiated power normalized over the unit sphere in these cases. maybe this should be U in this notation. Sometimes I call it P, sometimes I call it U here. So in some ways, the radiation intensity divided by its average value, and that is the directivity. If we don't write out these angles here, we typically mean the maximum value of it. And if you just see an antenna, like people could take this dipole and they would say it has a directivity of 1.64, that is the maximum value that comes out. But it's lower in other angles. The gain is then a third parameter, which says how is the radiation intensity related to the input power to the antenna. So the power accepted by the antenna, which means that the gain includes losses in the antenna. So if you have ohmic losses of it, your gain is then some number below the directivity. If the antenna is lossless, it would be it's equal to the directivity. And efficiency is precisely that quotient. So how much is the total radiated power compared to the accepted power by the antenna? That is called efficiency. So one example here, we will soon quit this. If we now take our short dipole and we look at the directivity of that one, this is precisely what we will calculate on Thursday. So that will determine what the directivity of a dipole is. We will figure out is 3.2 sine square theta. And that is this pattern that you see here. You can see a movie which is very slowly here, moving out here, no radiation up here. And the typical plot of this is this polar type plot. Here it is in 3D, here it's a cut of it. And when you read this off, what you should do is you say, what is then the radiation or the directivity at 60 degrees? Then you go to 60 degrees here, and you go down to this point, and you can see it's like 0.maybe 95 or something. If you go to 30 degrees, it's 0.3. If you go to 90 degrees, it is 1.5. And of course, if you go to 0, it is 0 here because it doesn't cut this. And that is what's plotted here in this 3/2 sine square theta. And that is what this one shows too. So the yellow color here is the highest, but it's also the distance to the center of this one that says what the directivity is. And this is a typical donut in shape in some ways. We will see it all the time for these dipoles. But of course, you have to be able to interpret the pattern that comes out. And when we go to the receiving antenna as the last thing, or second to last things, they have very similar properties. And for them, we will define what's called effective area, which says what is the received power compared to the incident power density. And if we take that quotient here, we get the effective area of the antenna. And by reciprocity, that is related to the gain of the antenna. So if you know the gain of the antenna, you know the receiving properties of the antenna, which says how much power can we receive of this for a given incident field. And the last thing for today is then Friis transmission equation. I will come back to that on Thursday, but that connects here your basic communication system, where we can actually compute what is the received power from a transmitting antenna with some power, antenna gain, effective area of the transmitter, the same thing of the receiver. And what we can do here is that we can determine what is the incident power density at the receiver, the radiation intensity divided by R2. We can then use that the gain is related to the radiation intensity to write this in the gain. And then we have the incident power density, which we then can receive to the received power. And that gives us precisely these things that is called Friis transmission formula, which some of you have seen before. And that says that the received power is the transmitted power, the product of the gain of the antenna, and then divided by 4 pi r, and r normalized with the wavelength here squared. That is Friis transmission equation. We will generalize this one, and we will come back to this one in the course. So we will not talk about this coordinate system here. So instead, we will go to the next lecture. And the next thing that happens is that on Wednesday, we have an exercise, which will practice on these things, so these antenna parameters. And then on lecture 2, we will look at these dipoles. We will derive what the directivity is and how we get currents to radiate. We will look at all of those parts, look a little bit more on using these antenna parameters. So for the exercise here, of course, read these lecture notes. Orphanides chapter 15 and 16. You have the instructions on Canvas on the PDF file. And before the exercise, the best thing is, of course, if you look at that before yourself. And then lecture 2, as I said, dipoles, different type of dipoles, and how we actually understand how currents radiate and what field they can give out for these cases. Okay, so that means it's time to end. So I know I rushed it a little bit here in the end. Sorry for that. But if there are any questions, let's take the questions now.